So hi everyone, so welcome to the first CSP seminar series. So for this we start with our internal speaker, Salar from Industrial Engineering Department. So Salar is assistant professor at IOE, and he received his PhD and master degree from UC Berkeley. And we also happen to be alumni from Columbia as well.
Yeah.
Yeah, Salar did some great work on I know some subgradient methods recently, and he's an expert on optimization and machine learning for structured problems. So today, let's welcome him to introduce his recent work on the blessing of nonconvexity on factorized problem. Thanks so much.
Thanks, Jing, for very kind introduction. Hello, everyone. I see a lot of familiar faces. Thanks for attending my talk. The title of my talk is Blessing of Nonconvexity in Factorized Model. I am from the neighbor department right here, IOE, and this is a joint work with my star student, Jen Hauma.
Sorry, so I think we need to share a screen because I only see you.
Oh, yes, that's a very good point.
So share yours. Yes.
I think on the Zoom.
I think I can do that here.
You do like.
But I'm not the host.
Are you the host, Ching?
If you give me the host.
Allow sharing.
Yeah, I need to make sure that.
Or co-host. Yeah, make me co-host.
Sorry, it's first time doing this.
No, I also struggle with Zoom. Okay, yes. All right. Okay. This is not my first time using this. All right. So let's get started. As you all know, a lot of learning tasks in today's data science involve solving an optimization problem in almost real time and in larger scale. The problems range from different board games, such as AlphaGo, all the way to some safety critical applications, such as autonomous driving. Now, one thing all these problems have in common is the underlying nonconvexity. In most of these problems, our goal is to fit a nonlinear model to a bunch of data samples that are collected with some possibly noise. And the underlying nonlinearity in the model gives rise to nonconvexity in the corresponding optimization problem. So the question is this nonconvexity an issue for us to solve these problems efficiently in practice and in theory? Now, depending on who you ask these questions, you may get different answers. If you're on the theoretical side, you would probably say solving nonconvex problems are very difficult in their worst case. In many cases, the main reason behind the difficulty of these problems is the fact that there is no efficient way for us to distinguish between local and global solutions. If you ask the same question from practitioners, you would probably hear answers like training nonlinear models is easy, just use SGD. So the question must be asked, why is there a gap between theory and practice? Now, to answer this question, we need to go one step back and see why we like convexity in the first place. Now, one good thing about convex optimization is that simple local search algorithms, such as gradient descent, are guaranteed to converge to a globally optimal solution under some conditions. Now, the bad news is most optimization problems in machine learning are non-convex, so our local search algorithms may get stuck at a spurious or bad local minima. Now, despite this non-convexity in practice, we use local search algorithms all the time. For example, gradient descent, different variants of gradient descent is the main algorithm for optimizing neural networks. And in many cases, these local search algorithms work pretty well in practice. And in some cases, actually better than their convex models. So here, this non-convexity is not really a curse for us. And in fact, in some cases, it turns out to be a blessing. Now, this observation actually very recently gave rise to a new paradigm in optimization, which is called benign landscape, or problems that are devoid of or free of spurious local solutions or undesirable suboptimal solutions. So the real question is not about convexity versus non-convexity. It is about whether or not we have local solutions, bad local solutions in the problem. Now, this leads to another question. Do we have benign landscape in optimization? Now, it's very recently a series of, I would say, breakthrough results in machine learning tried to answer this question. They showed that under some conditions, certain optimization problems in machine learning, such as low-rank matrix factorization, robust PCA, dictionary learning, and so on and so forth, they are free of spurious local minima, so they have benign landscape. Now, these are very important theoretical results because they actually helped us to move away from arguments only based on convexity versus non-convexity. But if you dig deeper, you'll see that almost all of them rely at least one of these conditions. They either assume that the loss function is smooth, or the data is almost noiseless, or we know exactly how many parameters we need to model our problem, or they hold locally around a neighborhood of the true solution, okay? But in practice, the bad news is that we almost never satisfy these conditions. For example, a lot of loss functions in machine learning, they're non-smooth. Here on the right, you see the landscape of a neural network, which is highly non-smooth. Even in the simpler cases, this is the landscape of a robust PCA problem. It is also non-smooth. Another issue is that in almost all instances, we have noise. Sometimes this noise can be adversarial, can be very large. And the other issue is that we don't know the true model. We don't know how many parameters we need to model our problem. So we have no choice but to overparameterize just to be safe. Okay, and also we don't know where the true solution is, true model is, so we cannot take advantage of this local benign landscape of the problem. In practice, all we can do is to just maybe do small initialization or random initialization and hope for the best. Okay, now the question is, can we relax these conditions and still have benign landscape? Now, it turns out the answer is no. Here I show a very simple instance of robust matrix recovery with a little bit of noise and a non-smooth loss. And I show you the performance of subgradient method on this problem. Here you can see that if I run subgradient method with small initialization, it will converge to a solution that is not global. It's a local solution and it's suboptimal. So here we don't have benign landscape because we have a local solution that is not global. What is even more interesting is the fact that this local solution on the training loss is in fact the solution that we care about because it gives us a better test loss. So not only do we have suboptimal local solutions, in this case, the global solution is actually the spurious solution or the undesirable solution because it turns out that it overfits to noise. Okay, so this is a phenomenon that cannot be explained using the notion of benign landscape. Okay, so the question is, why does subgradient method succeed despite the absence of benign landscape in this problem? So to answer this question, our approach to move away from arguments based on global benign landscape analysis and focus more on the solution trajectory of the algorithm. And the main reason behind that is because, well, benign landscape is very restrictive because it must hold globally over the entire landscape of the problem. Our algorithm takes a specific path, and therefore it is blind to whatever happens outside that path. Okay? Now, to do that, I'm going to focus on a special class of optimization problems in machine learning, which we call factorized models, or they're also called linear neural networks. So what is a factorized model? We assume that the output yi is the inner product of the input xi and the product of L weight matrices or parameter matrices, W1, W2, all the way to WL. And we also assume that the measurements are corrupted with some noise. Okay? This is the model we consider. Why do we consider this? Well, the first reason is that it already includes several very well-known optimization problems in machine learning. For example, low-rank matrix recovery, deep linear regression, deep neural networks, matrix completion, robust PCA, and so on and so forth. And the other reason is that we actually can use this as a test bed to analyze more general nonlinear neural networks, such as maybe neural networks with ReLU activation functions. Okay, and here we consider a non-smooth loss function. Specifically, we consider L1 loss, and the main reason is because L1 loss is more robust against outliers. I'm going to come back to this point later. And we're going to consider perhaps the simplest possible algorithm for solving non-smooth optimization problems, which is subgradient method. At every iteration, we take an element from the subdifferential of the objective and move towards the opposite direction, negative of that. Is there any question about the model? All right, so this talk is going to have two parts. The first part, we're going to talk about the problem of robust low-rank matrix recovery. This is based on the following recent papers on the topic. Then after that, we're going to extend our results to more general deep diagonal neural networks. Okay, so what is a robust low-rank matrix recovery? It is the problem of recovering a low-rank positive semi-definite matrix M star given a bunch of linear measurements of this form. Okay, here M star is the matrix that we want to recover. We assume that it's low rank, the rank is R, and R is significantly smaller than D. The matrices A1, A2, all the way to AN, they're known as measurement matrices. They define the measurements that we have, and this epsilon here is a noise vector. Okay, specifically, we're going to consider two different noise models. One is the outlier noise model. We assume that P fraction of the measurements are completely wrong because of the noise. And the second noise model is the Gaussian noise model. Every measurement is corrupted with some Gaussian noise with some variance. Okay, now the classical approach for solving this problem is based on convex relaxation. To get rid of the non-convexity of the problem by dropping the rank constraint and instead penalizing it in the objective. Okay, now one good thing about the convex relaxation technique here is that it's convex, so we can get global guarantees. But the bad news is that we need to essentially solve a larger scale semi-definite programming, which quickly becomes intractable with the scale of the problem. Another approach is to resort to this factorized model. It is also known as, or famous for, Montero Approach. The idea here is to write M as UU transpose for some low rank matrix U, that is D times R. So we implicitly capture the low rankness of M and directly optimize the loss based on this factorized model. Okay. Now, the good thing about this approach is that it's low dimensional. Instead of optimizing over a large matrix M, we're optimizing over a skinny matrix U. But the bad news is that now we have a non-convex problem to deal with, so we may not be able to get global guarantees. Another problem here is the fact that in many cases, we don't know the true rank of the solution. We don't know the true solution, so we don't know the rank of it. Okay, so we have no choice but to overestimate it. Okay, so we overestimate it with some R prime that is greater than or equal to 0. That leads to the overparameterization in our problem. And in fact, in some cases, our model will have the capacity to overfit to noise. Okay, now before talking about the theoretical results here, I'm going to show you some simulations. Specifically, I'm going to show you the performance of simple subgradient method on that factorized model. Okay, so here we assume we run subgradient method with initial point that is alpha times b. Alpha is an initialization scale and b is a orthonormal matrix. And the step size, we assume that it's exponentially decaying. Okay, so here we consider a very simple instance of the problem where the true rank is equal to 3, and we range the search rank R prime from 3, which is the exactly parameterized setting. Here we assume that we know the true rank, all the way to 20, which is the fully over-parameterized setting. We have no assumption on the search rank. We have no assumption on the rank of the true solution. Okay. Now it seems like in this case, turns out that subgradient method is completely agnostic to the over-parameterization level. So here you can see that no matter what R prime is, it seems that subgradient method, the error for the subgradient method, decreases at a linear rate until we hit some estimation error. Okay, so here subgradient method is agnostic to the overparameterization. Okay, let's see the behavior of subgradient method with respect to the initialization scale. Again, remember this alpha is the initialization scale, which is a norm of our initial point U0. Again, we consider the same instance. We assume that the true rank is 3, and we consider the fully overparameterized case where R prime is equal to 20. Here you can see the performance of subgradient method for different values of alpha. You can see that as we reduce alpha, the final error gets better and better. In fact, it seems like the final error somehow is proportional to this alpha right here. So if you want to have a small final error, all I need to do is to pick a small alpha. Okay?
Noiseless data here, right?
What's that?
Noiseless data.
It is noisy.
Noisy? How do you
Yes.
get very, very small amounts of noise?
It is very large noise. I'm going to get back to that.
How can you have a Frobenius norm at 10 to the minus 14th with large amounts of noise? Sorry.
L1 loss. So what we do, here it is. So I'm going to get back to that point.
Okay.
Okay, so turns out the good performance of subgradient method extends to the case where we have noise. Okay, so here you can see that subgradient method with the small initialization is robust against noise, even if up to 40% of the measurements are wrong. So here you can see this orange line. It is 10 to the minus 8, and 20% of the measurements are completely wrong. Okay.
I think X star must be the latent noiseless X.
Yes, yes, the low rank. Sorry, that is M star.
Yeah.
That is the M star that I talked about. So
Okay.
yeah, good point. All right. What is even more surprising is the fact that this subgradient method over L1 loss is robust even against Gaussian noise. Now, traditionally, L2 loss is usually used to recover the solution when you have Gaussian noise because of the fact that it corresponds to the maximum likelihood estimation. So here you can see that subgradient method over L1 loss has a comparable performance to gradient descent over L2 loss. So in some sense, subgradient method is better with L1 loss is better because it can handle both outlier and Gaussian noise.
Can you remind me what's X star?
X star is the M star. Sorry for the typo. So this is the true low rank solution that I want to recover. Okay, and remember, this is all these instances are overparameterized. So here, U, the rank of U is not necessarily the same as the rank of M star. Okay, any other question before I move on?
Also, when you look at UU transpose, are this like, do you look at the singular values of those? Are they like R large ones and?
No, they automatically converge to a solution that is low rank. So
Right.
all I need to do, run subgradient method on this. This U is in fact D times R prime.
Right.
Okay, start with a small initial point. Okay, it will learn, the algorithm will learn the R top singular values without actually increasing the small ones. And that the small initialization is critical here. I'll get back to that. Okay. All right.
And so can you provide some intuition why for Gaussian noise L1 norm works better than L2? Because L2 is
L2 actually works slightly better.
works slightly.
Slightly better.
Oh, okay, I see.
So L2 actually works slightly better. And I'm going to talk about the comparison later.
You see that the accuracy achieved on the Gaussian noise much worse than in the outlier noise, right?
Yes. In fact, when you have Gaussian noise, there are some information theoretical lower bounds on the solution. So you cannot recover a solution that has, say, like epsilon error, where epsilon goes to like 10 to the minus 14. I'm going to talk about that. So I'm going to talk about all these points.
Stagnation for Gaussian is because saddle points. I mean, you have some-
No, I mean, it's because of the variance of the noise.
Oh.
You can't go beyond this, like using any method. It's almost minimax optimal to some
I
sense.
mean, on the left hand side, there's some stagnation.
Here?
Left, yeah.
Oh, these are, yes. These are when you pass through saddle points.
Oh.
When you pass through, so again, I'm jumping ahead. You learn singular values one at a time. So if you learn the first singular value, if the other singular values are small, that's actually a saddle point for you. So it will take you some time to escape that saddle point. But eventually you will escape and you will converge to the true solution. All right. So again, I want to emphasize here that we do not have benign landscape in this problem. Okay. We may have suboptimal local solution and even spurious global solutions or undesirable global solutions. But it seems like when we run subgradient method on L1 loss with noisy measurements, what it implicitly optimizes is the error, the distance between UU transpose, the model that we are optimizing over, and this M star. Okay. Now, one way to explain this is through this notion of norm preserving property. Now, this is at the backbone of many results, especially in the context of low rank matrix recovery, because it turns out if the linear measurements are norm preserving, then gradient descent converges, or different local search algorithm, in fact, converge to true solution. Okay. And in fact, one special case of this norm preserving property is called the famous L2 restricted isometry property, or L2 RIP, which basically says that the linear measurements should be nearly isotropic for any rank R matrix M. Again, this is a very important condition that people usually use, again, in the context of low rank matrix recovery. But a fundamental issue of L2 RIP is the fact that it is completely blind to the nature of the noise. Okay, I'm going to explain it with a figure here. Here you can see the trade-off between the noise variance, okay, and the number of samples we have when the measurement matrices are Gaussian. Okay, because L2 RIP is completely blind to the nature of the noise, it will be satisfied. Okay. No matter what the noise variance is, it will be satisfied as long as the number of samples is above some certain threshold. Okay, but it turns out that L2 loss function will probably fail to recover a true solution if the number of measurements do not the number of measurements does not scale with the noise variance. Okay, now this is the fundamental shortcoming of L2 RIP because it is blind to the nature of the noise. It's overly optimistic. It cannot tell us when this L2 loss fails. Okay? Yep.
What's the norm for A of M?
This is two norm. This is a vector. This is a linear operator. The output is a M dimensional vector. M is the number of measurements. So this is the summation of squares.
Okay, not squared.
Yes. Any other question? Now, how can we go around that issue? First, I would like to argue that when we have noise, we never have, the measurements are never norm preserving, even if the number of measurements go to infinity. To explain this, first, I'm going to assume that for simplicity, let's assume that we don't have any noise in our measurements. And the measurement matrices are Gaussian. Okay, in that case, the expected loss, the expected value of L1 loss is exactly the error that we are trying to optimize. And this is, in fact, what subgradient method sees in practice. Okay, so one might say, maybe I can use some sort of uniform convergence result to show that the empirical loss will converge to this expected loss as we increase the number of samples. Turns out that the expected loss with noise will never converge to this loss, to this expected loss, even if the number of measurements go to plus infinity.
This is for Gaussian noise.
This is for any noise, but Gaussian measurements. So if your A1, A2, all the way to AM, they're Gaussian, because only in that case the expected value is going to be this.
Could be zero mean noise, any zero mean noise.
Any zero mean noise.
Yeah. Okay.
Yes, because the intuition here is in L1 loss, even if you have zero mean noise, the L1, the absolute value is going to make it non-zero mean.
Okay.
Right?
Yeah.
But so that is, looking at the norm preserving property in this setting is not the right approach. Turns out a better approach is to look at the direction of the subdifferentials. Okay. we're going to write the subdifferential of the loss function as a summation of two terms. The first term is the subdifferential of the expected loss over here, and the second term is the subdifferential deviation. So if the subdifferential deviation is small, that basically means that this f and f bar, they're aligned. Okay? Now, we say the measurements are direction preserving, not norm preserving, but direction preserving if the subdifferential deviation is small. Okay? I'm going to make it slightly more formal. We say measurements are, they satisfy sine RIP with parameters r and delta if this subdifferential deviation is upper bounded by the norm of u times delta for any u that is at most rank r. Okay, and the reason why we call sine RIP is because, well, take the derivative of absolute value, you get a sine function. Okay. Now, a fundamental result here is the fact that when we have noise in our measurements, the measurements are not norm preserving, but they will be direction preserving. Okay, I'm going to make it formal. First, we assume the outlier noise model. We assume that p fraction of the measurements are completely wrong, very large noise, and measurement matrices are Gaussian. Then we can show that we satisfy sine RIP with high probability with parameters r and delta if the number of samples is lower bounded by d times r divided by 1 minus p squared. This p is the corruption probability times delta squared. So this implies that the measurements are going to be direction preserving even if they're corrupted with arbitrarily dense and arbitrarily large noise value, provided that n scales accordingly. Okay? And in fact, we can extend this to the Gaussian setting. Okay? In the Gaussian setting, when I say the Gaussian setting, I mean the noise is Gaussian. If the noise is Gaussian, okay, same statement holds, but in this case, the lower bound scales with the variance of the noise. Okay, and that's important. Now, turns out the notion of sine RIP is exactly what we need to establish the convergence of subgradient method. We prove that if the measurements satisfy sine RIP with parameters delta and 4 times r, here r is the true rank, not the overparameterized rank, the true rank of the solution. And I'm going to explain where this 4 comes from. Then subgradient method with small initialization will converge, and exponentially decaying step size will converge to the true solution, in fact, with an error that scales with alpha. Alpha is the initialization scale. Okay, I'm going to make a few observations based on this.
Sorry, is that the outlier noise or both together or the gas?
Doesn't matter as long as you satisfy sine RIP.
Okay, yeah, got it.
So that's a good point. I'm going to get the second point I'm going to make is exactly that. First observation is that our result is independent of the search rank, R prime. Nowhere in this theorem do you see any trace of R prime. Okay, R here is a true rank, and that is also in line with our simulations. We show that no matter how big R prime is, we get convergence, and it doesn't really affect the performance of the algorithm. The other result, the other implication here is that our theorem, the theorem that you see here, is independent of the noise as long as you satisfy sine RIP. So we capture the effect of the noise through this notion of sine RIP. Okay? And the third point that I'm going to make is the error scales with the initialization scale. And this is, again, in fact, in line with our simulations. We show that if alpha is small, then the final error is going to be small. Same here. The upper bound scales down with alpha. All right? And in fact, we can turn this into a convergence rate result. We show that given any precision, epsilon, suppose that this is only for outlier noise. Given any arbitrary precision, subgradient method with small initialization will converge to an epsilon accurate solution, provided that this alpha initialization scale is proportional to epsilon, and the number of iterations is going to be polylogarithmic. So this is a near linear convergence result. Okay, it's not sublinear; it is near linear. All right.
Can you The exponentially decaying step size surprises me. I'm used to like a harmonic decay because that's going to be finitely summable, which I think for subgradient descent we usually don't want it to be finitely summable. Could you give me a
very good point. Turns out, if you look at the subdifferential here, subdifferential has a self-normalizing property. If I go back to, so I'm not going to show it here. It turns out that no matter how close you are to the optimal solution, the norm of the subdifferential is going to be around 1.
Huh.
So if you want to get linear convergence, you need to have exponentially decaying step size. I mean, you can get 1/k, but then your convergence rate is going to be sublinear.
So that's some combination of the L1 and maybe the nature of your sensing matrices having these.
Exactly.
Okay.
So look at that. So let's look at the subdifferential of this, right? If you take the derivative, the denominator is going to have a Frobenius norm,
Okay.
right? And that is the self-normalizing property that I'm talking about. Okay, but all right. Okay, to give you some insight, I'm going to compare our result with existing literature, both in terms of iteration complexity and the sample complexity. First, in the outlier noise model, we know gradient descent with L2 loss does a terrible job, and there is no convergence guarantee in that case. When we know the rank, meaning that R prime is equal to R, a recent result showed that subgradient method with a special initialization will converge to the true solution at a linear rate. If we have overparameterization, Jing and his collaborators have shown that subgradient method with a special initialization will converge to the true solution at a sublinear rate, which is exponentially slower than log of 1/epsilon. Here we show that this, if we consider subgradient method with small initialization, we will get a near linear convergence result, and that is independent of the search rank. Okay? And we could also extend this to the Gaussian setting. In the Gaussian setting, it is known that gradient descent on L2 loss will converge in the exactly parameterized regime. It has log of n divided by d iteration complexity, but it also slows down when we have overparameterization. Okay, and to the best of our knowledge, we don't have any result under Gaussian noise model when we use subgradient method on L1 loss. Again, we see a similar kind of benefit when we use subgradient method with small initialization. We have a near linear convergence result. One thing I want to mention is that because of some information theoretical lower bounds, we cannot get epsilon accuracy here. In fact, minimax error here scales with square root of d times r divided by n. Here r is the true rank, not the overparameterized rank. It is a true rank. The best known result for gradient descent with L2 loss has an error that scales with r prime. R prime is the search rank. So in the overparameterized regime, there is a huge gap between these two, right? Our result almost closes this gap, not exactly, but almost closes this gap. We show that subgradient method with a small initialization on L1 loss has an error that is higher than this lower bound by at most a factor of square root of r. Okay, and that is for the Gaussian noise, obviously. Any questions so far?
There's a
Where in the algorithm did you use search rank?
What's that?
I mean, the search rank. Can you remind me where in the algorithm search rank is?
Search rank is the dimension of U, the number of columns in U. If I don't know the rank of the true solution and I overparameterize, okay?
So
It's
it's
a selected rank. He's not searching. He's picking a rank.
yeah. So, but in formulating the problem, you are pick an R prime.
Right.
Yes. All I need to have is R prime greater than or equal to R. Can't be 2 times R, can be 10 times R.
So practically you just choose maybe some big R.
Well, but you should keep in mind that if you pick large R, you lose the whole point doing factorized model, because if R is equal to D, then you're optimizing over a D by D matrix, right?
Yeah, so, but still implicitly in your algorithm, you need to like pick an R prime that is like bigger than the ground.
Yes.
Although you
Yes.
we assume it to be unknown.
Exactly. But if you don't know anything about that R, you can just set R prime to be D. Sure, you're going to have a D by D matrix, but I would argue that it's better than STP still, right?
Yeah. But the R is larger, the iteration complexity is smaller under a Gaussian noise model, right?
The iteration.
You said square root of R worse, but it looks like R worse in this. Or no, I'm wrong. Never mind.
So yeah, so here the lower bound, I mean, our error is higher than this lower bound by a factor of square root of R. But I mean, obviously, if R is equal to R prime, then gradient descent on L2 loss is better. Okay, but here we talk about the overparameterized regime. Any other question?
So there's one question from the Zoom audience. Can you explain more on small initialization? Would it be better to have a alpha that scales the initialization to have similar range, but I think it's meaning similar norm as a minimizer?
Not necessarily. And I'm again, the small initialization is the key, because maybe if I explain the proof, it would be, I'm going to give you a very high level idea behind the proof, and I'm going to explain why small initialization turns out to be the key idea here in our ability to recover the true solution. But yes, you cannot replace alpha with the norm of, say, true solution, if that's the question.
Yeah, I think so.
Yeah.
Could you remind me what N is?
N is the number of samples. This is the iteration complexity. Next, I'm going to talk about sample complexity, or the number of samples I need to guarantee small error. Okay. In the outlier noise model, for overparameterized regime, the best known sample complexity, again, shown by Jing and his collaborators, is D times R prime to the power 3. Okay. Again, in the overparameterized regime, this can be very large. Okay. Our result shows that no matter what the overparameterization is, the sample size that I need scales with the true rank, not the search rank, but the true rank. Okay. The other thing I want to mention is that the existing results, they all rely on either the global benign landscape or to some extent local benign landscape. And because of that, they have very restrictive upper bounds on the corruption probability. For example, they assume that P is upper bounded by 1 over square root of R prime. R prime is the search rank or the upper bound for the rank. We don't rely on the benign landscape. So this P can be arbitrarily close to 1. Again, the number of samples should scale based on that, but we don't have any upper bound, any explicit upper bound on P. And we can get a similar improvement, again, in the sample complexity for the Gaussian noise model. All right, any questions? Okay, I'm gonna give a brief overview of the proof then. As I mentioned at the beginning, our idea is to move away from global landscape analysis and have a fine-grained trajectory analysis for our used algorithm. Okay, the way we are going to do that is by decomposing our solution trajectory into 2 terms, signal term and the residual term. Okay, the signal term is the projection of every iteration of our algorithm onto the column space of M star, the true solution. We show it with ST, and its orthogonal complement is the residual term. We show it with ET. Here, V is the eigenvalues corresponding to the non-zero eigenvectors corresponding to the non-zero eigenvalues of M star. Okay, so it has R columns. All right. Now, based on this decomposition, it turns out that the final error can be upper bounded in this form. It's a summation of 3 terms. The first term is the distance between SS transpose and sigma. Sigma is a diagonal matrix that collects all the non-zero eigenvalues of M star. So it's an R by R matrix and it's diagonal. We call this the signal term, okay? And we have cross and residual term, all right? our goal, so at the beginning, when we have small initialization, right? Both ST and ET, they're small. So the error is dominated by the first term, and that is also dominated by the norm of sigma. Okay, so at the beginning, this is how the upper bound on the error would look like. Cross and residual terms are small, they're in the order of alpha. The signal term is in the order of sigma. Okay, our hope is to show that as we make progress in the algorithm, this signal term converges to 0 while having a small value, value for cross and residual term. If we can establish something like this, then we're done. The upper bound here is going to be, the upper bound here is going to be in the order of alpha. Well, the bad news is when we run the algorithm, the residual term has a non-monotonic behavior. It blows up before going down. So here, this orange curve is the residual term. You can see that it goes up first before going down. Okay, so to analyze this non-monotonic behavior, we need a finer decomposition for our solution trajectory. This decomposition is going to be dynamic, meaning that at every iteration, we're going to project this ET, residual term, onto the row space of ST and its orthogonal complement. The projection onto the row space is shown with FT, and the orthogonal complement is shown by GT. Now, the first question is, why do we do such decomposition, right? Turns out that if we do this decomposition, the non-monotonic behavior of ET is only because of FT and not because of GT. GT remains monotonically increased, but the increase is up to 10 to the minus 8. What actually has a non-monotonic behavior is FT. But turns out that FT is low rank. In fact, its rank is exactly R, no matter how big your overparameterization is. The rank of FT is R. So I can essentially control this using the notion of sign RIP because it's low rank. The second term is the high rank term. This rank, the rank of GT is going to can be as big as R prime, but turns out we can control the norm of this GT, and we can show that it remains in the order of alpha. Now, putting everything together, the final error can be written as a summation of 5 terms. Okay, the details don't matter here. What is important is the fact that the first 4 terms here, they're all their rank is R. They're independent of the search rank. They're at most rank R. R is the rank of the true solution. So their summation has rank at most 4 times R. And that's why we need sign RIP with parameters delta and 4 times R to control these 4 terms. The last term turns out, with some math, you can show that this remains in the order of alpha. Okay? That's the intuition behind the proof of this theorem. Okay? Now, next I'm going to move on to the second part of this presentation. This one is going to be shorter, which is deep diagonal neural networks. Okay, so what is deep diagonal neural network? It is also known as deep linear regression. You assume that the true model is a simple linear model. Okay, yi is equal to inner product of xi and the true parameter theta star, and yi is corrupted with some noise. Here we assume that the noise is outlier, and theta star has at most k number of non-zeros. So the true parameter is sparse. Okay, the model that we consider here, it has this form. It's the inner product between x and the entry-wise product of L vectors. So this is the L entry-wise or Hadamard product between L vectors, W1, W2, all the way to WL. Okay, and we also again consider L1 loss function, and again we analyze the subgradient method. Now, the first question is, why are we considering a deep model for something that appears to be simple linear regression, right? I'm going to explain it through some simulations. Here, our goal is to look at the landscape of the problem around the true solution at theta star. I'm going to look at 2 directions. One is the most descent direction from the subdifferential, Okay, and this alpha basically says how far we go towards that direction. The other direction is H. That is the most negatively curved direction of the landscape at theta star. Okay, and theta shows how far we go towards that direction. Let's look at the one layer model. One layer model means that we only have W1, so that is a convex model, simple linear regression, nothing fancy about it. Okay, if we have outlier in our measurements, turns out that the true solution is nowhere close to the globally optimal solution of this problem. And in fact, here you can see that this is the true solution. These are the directions. You can see that the loss goes down in two directions.
Okay. L1 loss again now?
This is L1 loss again. And subgradient method, in fact, completely misses the true solution. You can see that here, this is the empirical loss. It goes all the way to 0. But the generalization error, and by generalization error, what we mean is the distance between the solution we get and theta star, it doesn't go down, right? Now, let's see what would happen if you add one more layer. Let's see what would happen if you add one more layer here. Well, we lose convexity for sure, right? We go from one layer to two layer model. But turns out that if we add one more layer, the true solution emerges as a local solution on the landscape. And in fact, it becomes a stationary point. Not only that, if I run subgradient method with small initialization, I will converge to this true solution. Okay? What would happen if you add one more layer again? Problem becomes more non-convex, right? But still turns out that the true solution, theta star, remains as a stationary point of the landscape, and still subgradient method converges to that true solution, but now with a better accuracy. You can see that the final error is actually better than two layer. Now, this is again what we call as the blessing of non-convexity. By adding depth to the model, the problem becomes more non-convex, but somehow subgradient method actually performs better. Question?
Why does one layer model fail?
Well, you have theta star is sparse. That's the assumption. Okay. You have outlier noise. You can overfit. We're not imposing any sparsity structure on theta.
So the one layer solution is not sparse.
One layer solution is not sparse. The global solution is not sparse. Because you overfit. If the true model is sparse and you don't impose that sparsity in your model, your theta can be fully dense, right? So you essentially overfit to noise. Especially if the number of samples you have is in the order of dimension D. I'm going to talk about that. Okay, but when you have convexity, when you have a convex model, you don't have local solutions, right? And the global solution is the overfitted solution. But if you have non-convexity, you have the possibility of having a local solution. And if that local solution happens to be your true solution, and you have a way to converge to that local solution, then you're good. Okay, and in fact, we have a theorem that supports that. I'm going to wrap up very quickly. Turns out that's subgradient method. Again, if xi here is Gaussian, and a number of measurements scaled with k squared. K is the number of non-zeros in theta star. It is not a dimension. So k can be significantly smaller than d, right? And n can be significantly smaller than d, right? Then subgradient method with small initialization and small step size will converge to the true solution. The final bound doesn't matter. But the important part that I want to emphasize here is subgradient method provably performs better in deeper models. So if L is the number of layers, is greater than 3, greater or equal to 3, then the final error is going to be provably better than compared to the case where L is equal to 2. Okay, what is even more interesting is the fact that the final solution will be balanced in a sense that every single layer of the trained model is going to inherit the same sparsity pattern as theta star. Okay, all I need is to have the multiplication to be theta star. Here, the theorem says every single layer is going to have the same sparsity pattern, and their difference is going to go to 0. Okay. Now, turns out that we can actually convert this.
Question. So the depths, I mean, if you increase in depths, you will get better performance, or is that you 3 or
3 turns out for linear regression, 3 is the threshold. Turns out if you increase beyond 3, you don't get significant improvement. And the reason is really because the underlying model is very simple. You don't need a very deep model to capture linear regression, right? So beyond 3, the gain is very marginal. But between 2 and 3 and beyond, there is a shift.
So in your curve, you observe an overfitting from L equal to 2. Do you like also observe overfitting for 3 or 4?
No, so we don't see overfitting in 2. In 1 layer, we see an overfitting, right? Because we converge to the globally optimal solution. Globally optimal solution is the same in all of these models, but the local solution is the solution that actually helps us to recover the true solution.
So to make this curve, you needed to choose an n that was sufficiently large, according to the next slide, and that n has a c in it. Do you know that constant? So you can choose.
Well, that's the. It can't, like, it's a large C, and I'm hiding all the logarithmic factors, by the way. So we have polylogarithmic factors flying around. Yes. But we can convert this into a convergence rate result again. Now, the benefit, I said, if you have a bit deeper model, you get a better final error. But turns out, if you have a deeper model, it will take you longer to train it. Okay, so here we actually find a convergence rate exactly for arbitrarily deep linear diagonal linear neural network. The convergence rate ranges from 1 over epsilon for 2-layer model, all the way to 1 over epsilon squared for infinitely deep model. So it can be, and in practice, it is definitely the case. We need longer iterations to converge in deeper models, but once you converge, the solution is going to be better. Okay, now again, I want to mention that here we don't have benign landscape. Okay, and in fact, we have a deeper result, turns out, for deep linear regression. We could show that if n is strictly less than or equal to d. Okay, so d is the dimension, n is the number of samples. Then with constant probability, and for any L greater than or equal to 2, none of the true solutions, again, by true solution, what do I mean by true solution? All the W1, W2, all the way to WL, such that their product is equal to the true solution. None of these true solutions are global minimums. Not only that, there exists at least one true solution from this set that is not a critical point or not a stationary point of the landscape. Okay, so that shows the fundamental shortcoming of benign landscape, because benign landscape gives you a very holistic overview of the landscape. It is always the worst case. It is governed by the worst case solution. Here, the worst case solution is very bad. It's not even a critical point, right? But despite that, turns out that among all these true solutions, it's not unique, because that set W has infinitely many solutions. The one that is balanced, again, the one that has the equal weight, different layers, turns out to get flatter and flatter as you increase the length, as you increase the depth. Here, it's just considered a ball around that balanced solution. This is essentially the slope of that bound, and it becomes flatter. It becomes smaller and smaller as you increase L. Okay, now that is the end of my talk. So to conclude, we mentioned that despite their non-convexity, many optimization problems in machine learning can be solved using local search algorithms, and that was the main motivation behind this talk. But we also mentioned the main shortcoming of the existing techniques to analyze these optimization problems. They were based on benign landscape, but benign landscape comes with a lot of fundamental problems. And our goal was to take a different approach and maybe look at the trajectory and the trajectory of the solution of subgradient method for a special class of optimization problems in machine learning, which are called factorized models. And our contributions are listed here. I'm not going to go over them. And with that, I would like to thank you for listening to my talk, and I would be happy to answer questions.
Any questions? Speaker. Thanks, Salar, again for the great talk.
Thanks for inviting me.
So for the first half, you had the results for the outliers, and you had results for Gaussian noise. Have you thought about or analyzed the case where you have Gaussian noise plus outliers, which is probably
yes. We believe that it is possible to combine those two. We haven't done it, but I think it is possible.
And then as a really small question, slide 24, are those Frobenius norms that are not squared?
Probably, I don't know. Let me go back. Which slide?
Right there, yeah.
Yeah, these are, no. These are operator norms.
Oh, operator.
I think these are operator norms, or maybe these are Frobenius.
The two is
no. These are Frobenius norm.
Okay.
Yes, because trace of this times itself transpose. Then yes, it is the Frobenius norm.
Should they?
No, they're not squared.
So I don't know where the two came from then. If it was square and you expand things out, I would expect a two maybe somewhere. But of course it's more complicated than that. I realize it's not just expansion.
No, I don't think we need two here.
Oh,
sorry. The square. No.
Just curious. That's what minor thing.
But I don't remember.
Is there orthogonal the terms, the cross term?
Yes, and they can, but these are not orthogonal, right?
Right.
Yeah. I mean, we can do the math. Yeah, I'm pretty sure that it's Frobenius norm first.
Yeah.
And the square, probably there is a square. Well, it doesn't really matter. If you don't have square, then all you pay is like a factor 2 on the right hand side.
All right. Fascinating. Thank you.
Yeah.
Can you remind me of the definition of sine R of the early pages?
Oh. Okay, yes. Sine RIP, basically the intuition behind it is if this subdifferential deviation is small for some gamma over there. So gamma can be arbitrary. The reason why we have gamma is because we want to look at the direction. It really doesn't matter what that gamma is. As long as this term, there exists a gamma for which this is small, that means that those two vectors align, right? So that is the definition of sine RIP. If we want to have, if it just happens that this subgradient deviation isn't small, then we say we satisfy sine RIP. And the formal definition here is this subdifferential deviation is upper bounded by norm of u times delta. For some delta, again, delta is a parameter for sine RIP, and R is an upper bound on the rank of u. So this is, you can see that this is, going to the next slide. Theorems like this, they are uniform results, meaning that they must be satisfied for any choice of u that is rank R. Okay. So yeah, I hope that it's clear now.
So the measurement matrices. So what notation did you use for measurement?
So measurements are the AIs. So going back to the model. Yeah, this AI. And that curly A is just a linear operator that captures AI inner product with its argument M.
So we need some special A that satisfy the sign RIP.
Yes. So that yes. Very good point. So sign RIP obviously may not be satisfied for an arbitrary choice of AI, but turns out that if it's Gaussian, then it is satisfied. For sub-Gaussian, we don't know yet. We still, it's like, again, our result crucially relies on the fact that AI is Gaussian, because for Gaussian, this is the expectation. Expectation takes a very simple form when AI is Gaussian. But I would say like all these results for RIP, they also work for Gaussian. So that's like a common framework for us to, compare different notions.
What about an entry-wise observation? So
It does
A
not
doesn't
satisfy sign RIP.
and it doesn't
No.
satisfy sign RIP.
Yeah. I mean, okay, if it does not satisfy RIP, probably it's not going to satisfy sign RIP, because sign RIP takes, it's like RIP plus some noise. So if you don't have noise and you can't satisfy it, then. But it might be the case. So again, like the notion is a little bit more general in the sense that we don't look at the norm. We only care about the direction. So maybe there is like another because when we have entry-wise measurements, the right notion is the incoherency. Maybe there is a counterpart for incoherency in this case.
So there's another question from the audience. Are these concurrent only hold for the subgradient algorithms? Say if we smooth one norm, I guess like a Huber norm or something.
That's a good question.
We get similar results.
Well, the notion of sign RIP is only for L1, right? And that comes from the subdifferential of L1. If you consider a different norm, maybe, but then we need to have a different kind of direction preserving property to impose based on that loss. So yeah, the results don't directly translate. Yeah.
So when you look at your last several slides, you mentioned about the flatness.
Yes.
So how do you characterize the flatness? I didn't quite catch.
So yes, let me.
And also, I mean, some reason like empirical work that if your loss, your mean matter is more flat, you generalize better. So your results somehow.
Probably. So the result we have does not directly imply better generalization, but let me go to this theorem here. So what is this? So suppose that W star is the balanced solution. So that W star is the collection of all these weights. Each weight is square root of, not square, Lth root of theta star, right? All these elements are the same. Okay, this theorem basically says, suppose that there's a radius, gamma, okay? If gamma is small, so we have an upper bound for gamma, I didn't mention here, okay? For sufficiently small gamma, this infimum, okay, is lower bounded by this value right here. So let's look at this as a function of depth, L, right? If I increase L, this goes down, becomes smaller, it becomes a larger negative number, right? And this is the most descent direction. So this guy here, right-hand side, captures the most descent direction from W star because it's the infimum, right? Over all possible directions. And the most descent direction scales like this. So if L is large, the most descent direction becomes small in norm, exponentially fast. Actually faster than exponential in this case.
6.
Yeah. I think there is another question.
Yeah, I was wondering, what's the intuition behind like the W's layers inducing the sparsity in the theta star? Why is that like What's the intuition?
Yeah, that's a very good question. Turns out that, but the intuition here is, again, if you start at a small initial point, you see something that is very similar to incremental learning that people always say in machine learning. You learn different elements of theta one at a time. You learn the largest one, okay, first, and the other elements remain close to 0. They remain in the order of alpha. And if you focus on only one element, then turns out that the problem becomes much simpler. In fact, you will converge. That one element is going to be the square, the nth root of theta star in that one element. Now you go to the second one, okay, second largest, and use the same argument. The main reason is because you learn different non-zero elements of theta star one at a time.
So if you run like vanilla subgradient descent, it will do this incremental automatically. Like you're not.
If this is the step size is small enough, yes. Yes, you can again, step size should be small. The initial point should be very close to the origin. Yeah.
So considering the solution you find is like the nth root. Now I'm assuming the true solution has to be non-negative here, right?
The one assumption I didn't mention, I tried to hide it, was that we assume that theta star is non-negative.
So
So the elements are, if it's not negative, then like you have this ambiguity about the sign. Yeah.
okay, so the extension to
The extension, we believe it is, I mean, we claim in the paper that is easy, but I think, yes, I think it is easy. So the idea over there is you're going to get like exponentially many, because you can consider like plus and minus signs. Any other question?
But you're saying if it is positive and you start with some value near 0, just you never go to like where W1 is and W2 are both negative, so the product cancels out?
No, you don't.
Interesting.
So, but initial point should be, alpha should be positive, right? You cannot, yeah.
So would you say the first part of the talk is also an instance of incremental learning in the sense of like you're
Yes.
picking up one singular?
Yes. Then you have incremental learning on the eigenvalues. In fact, we're working on an extension, led by my student, on what would happen if you have a general function. Okay, then like you have like you have to consider a function basis decomposition. Then you learn different function bases one at a time. Yeah. If you have more questions on that, please reach out to my student, John Howell. He knows better. All right, I think we are over time. Thank you. Yep.